Hey, welcome back. All right, we're taking a look at the second reasoning for the trends that we see on the periodic table today. So the first reasoning was nuclear charge. Today, 5.4, we're taking a look at electron shielding. Okay, so we'll start off with a little bit of review. So lithium, here's lithium with 3 positive charges. It's like a nuclear charge of 3. And 3 valence electrons. We're going to stay in period 2. Go to carbon. With a nuclear force of 6 and 6 valence electrons. And then we'll stay in period 2 again and go all the way across, and we'll take a look at neon. Nuclear charge of 10. Ten valence electrons. All right, so there we go. Again, this should look familiar. This is what we talked about yesterday. So as you move across a period, the atomic radius, that's the size of the atom, is getting smaller because the nuclear charge is getting larger. +3, +6, +10. So this isn't just me being a bad artist, which it is. I am a bad artist, but these atoms are actually getting smaller in size as we move across a period. The reason for that, again, is this increased nuclear charge. 10 protons are going to be able to pull those electrons in tighter than 3 protons. All right, so that's all review. Today, we're going to take a look at something else. So as we move down a group, if that nuclear charge holds, that's all the same, you'd expect, man, francium would be a tiny little itty bitty atom with 87 positive charges in the nucleus. It should be tiny, and it's not, because there's something else going on. So here's lithium, number 3. Let's take a look at sodium and then potassium below them. So sodium is +11, just like everybody else. He has 2 electrons in his first energy level. His second energy level is filled up then. And he has 1 electron in his third energy level. So he looks very similar on the outside to lithium. He's got 1 valence electron, just like lithium. All right, now below him then, there's sodium. Now we're going to do potassium, number 19. So +19 in the middle. Two electrons on the first energy level. Eight more on the second energy level. Potassium has his third energy level filled up as well. And he has 1 lone valence electron on the fourth energy level. And again, as you can tell, so potassium, sodium, lithium all have one valence electron on their outside energy level. But as you can tell, our atoms got larger, even though the nuclear force is getting stronger. So clearly, nuclear force is not just, or nuclear charge is not the only thing at play. As you move down a group, so all these elements are in the same group, they're all alkali metals. As you move down a group, the atomic radius, whoops, sorry about that, messing myself up there. Should the atomic radius increases down a group due to increased electron shielding. As you're moving down, the size is getting bigger because we have more electron shielding. Ah, there's the title of the notes. He said it. What exactly is electron shielding? Well, good question. So electron shielding is occurring when the inner shell electrons, the ones that aren't valence, are shielding the nucleus, and at the same time, they're repelling the valence electrons. So we kind of talked about, well, our theory or our phrase of the day yesterday was that opposites attract. The negative charge and the positive charge, those are attracted. Opposites attract. The phrase of the day today is that like charges repel. This negatively charged electron and these negatively charged electrons don't want to be anywhere near each other. They're going to push away from each other. And all these inner shell electrons are repelling this guy. Yes, he's connected to the plus 19. He is. But man, there are a bunch of negatives in between the 19, the positive 19, and this outside electron. And because of that, they're pushing him away, and your atom is getting bigger and bigger and bigger.
Theranos Sal, if you are in the building, please come to door 1. Your dad is waiting. Thank you.
So 2, 4, 6, 8, 10, 12, 14, 16, 18 electron shielding. 18 electrons are shielding the nucleus here. Versus we move up a level, we only got 2, 4, 6, 8, 10. Remember, it's the inner shell electrons that are doing the shielding. So sodium only has 10 electrons shielding the nucleus. That's why he's a little bit smaller. And we go up to lithium, only 2 electrons shielding for lithium, so that he's even smaller than the rest. So 2 is a lot smaller than 10, which is much smaller than 18. One last little note here then. The reason why we did not see this trend yesterday is because electron shielding does not increase across a period. It doesn't get any larger. As long as you're in the same period, you're going to have the same amount of inner shell electrons. You're not adding any additional inner shell electrons. You're only adding valence electrons. So Here's carbon. Carbon's in the same period as lithium, 2 electron shielding. Here's neon. He's got a whole bunch more total electrons, but he's only got 2 inner shell electrons, so only 2 electrons shielding. So that's why as we move across a period, the only real thing we're looking at is nuclear charge. The stronger that nucleus, the more he's going to pull in those electrons. But once we start going down the group, yes, we might have a greater nuclear charge, but we've also got more inner shell electrons that are shielding that nucleus from the outside electrons. So those two things are working together to give us the trends that we see on the periodic table. So we just looked at atomic radius. We've also got ionization energy. And very similar to atomic radius, well, the more shielding you have, the lower the energy. So here's lithium. Again, ionization energy is the amount of energy to remove 1 electron. So here's sodium, here's lithium. Again, they look very similar. They both have 1 valence electron in the S1. This guy's in 2s1, this guy's in 3s1. The difference is how many inner shell electrons they have. Only 2 electrons shielding the nucleus here, whereas we have 10 electrons shielding the nucleus here. 10 electron shielding means it's actually going to be easier to pull that electron away. He's not as attached to the nucleus. He's being blocked, he's being repelled by 10 other electrons. So his ionization energy really isn't that big, especially compared to lithium. It's going to have a smaller ionization energy. It's going to be easier. It's going to require less energy to pry away that outside electron. This guy, a little bit more energy. He's closer to the nucleus. He's not being shielded by nearly as many electrons. So the more shielding you have, the more repelled that outside electron is. And so the easier it's going to be remove them. Easier means less energy. All right, something we haven't talked too much about, and I love talking about it. So here we go. Multiple ionization energies. All right, so here's the idea. Ionization energy is how much energy to remove 1 electron. But what if we want to remove a second electron? Well, that would be our second ionization energy. How about if you wanted to remove a third electron? That would be your third ionization energy. So let's say you look at beryllium. It'd be nice and easy to draw beryllium. It's just number 4 there. There he is with his 2 valence electrons. So this is our beryllium atom. There's his electrons. And again, we're going to first pry off that electron right there.
Hello, this is another announcement. We're looking for Cano Fowl. Cano Fowl, your dad is at the front office waiting for you. If you are in the building, please come to door 1 where the buses come in. Your dad is here waiting for you. Thank you.
So we're going to go ahead and ionize beryllium. We're going to take 1 electron. This is what we call ionization energy 1, the first ionization energy. And it's going to be a bit of energy. He's at 2s2. That's a pretty stable configuration, but it's not a ton of energy. We can pull that electron away from beryllium, and we end up with beryllium plus 1 ion, 1s2, 2s1. Well, what if we take a second electron from him? We now end up with beryllium plus 2. We still have 4 positive charges in the nucleus, and now we're down to just 2 negative charges. So to take this second electron, again, is not going to be a huge amount of energy. We're going to call this ionization energy 2. And it's going to be a little bit bigger than ionization energy 1. But it's still not a huge amount of energy. Aha! Now we've removed the electrons from the second energy level. Now we're down to the first energy level. Take a look at what happened to our shielding. 2 electron shielding. 2 electron shielding. If I try to take one of these last electrons and remove it, so that'd be my third ionization energy for beryllium, my IE3, oh my goodness, how much energy would this take? There's no longer any shielding whatsoever. We are down to 0 shielding. That electron is not being repulsed, and it's not being pushed away from the nucleus by anything. There are no more inner shell electrons. We're now down to the inner shell. So now we're going to have this huge jump, an enormous amount of energy to remove that third electron. You're probably not going to be able to do it. It's going to be huge. Not so big ionization energy 1, not so big ionization energy 2, huge, 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 huge for ionization energy 3, because we went down an energy level and we lost a bunch of shielding. Let's take a quick look at aluminum. Same idea, aluminum. Where is aluminum's big jump going to come from? So 3 valence electrons for aluminum. Aluminum, the atom, 1s2, 2s2, 2p6, 3s2, 3p1. So here's what aluminum looks like. If we were to take this first electron right here, it's actually going to be pretty easy to take. That's our 1, 3p electron. Aluminum's not too upset about losing that one. So IE1 would be pretty low. Okay, next up, let's say we take this electron up here. Now it's going to be a little bit more difficult. We've got a full sublevel, 3s2, but it's still not a huge deal. And then finally, we'll take that electron there too. So we took a total of 3 electrons, and none of these is really a very gigantic amount of energy. So we're going to pull 3 electrons out of there. And look what we're left with. And this is going to be aluminum with a +3 charge. He lost 3 electrons. He still has the same number of protons, so it's now aluminum ion with a +3 charge. If we try to take a 4th electron, if we try to pull that electron right there off, it's going to be an enormous amount of energy. IE4 would be huge. Take this guy right there. Big reason why? Look at the shielding. Over here, for all 3 of these, we had 2, 4, 6, 8, 10 electron shielding. Didn't matter which electron we're taking. The first guy, 10 electron shielding. This one up here, 10 electron shielding. Third electron, 10 electron shielding. To take those first 3 electrons, we had 10 electrons shielding. To take that 4th electron, hey, look at this. Our valence shell has gone down. We had the 3rd valence shell. Now we're down to the 2nd valence shell. And now we've only got 2 electrons shielding as opposed to 10 over here. So this electron, that 4th electron we try to remove, is going to be so much tighter to the nucleus. Really, really, really strong with the nucleus. And that means it's going to take a ton of energy to pry him off of there. So all atoms are going to have this big, gigantic jump for their ionization energy after you go down a valence level and the shielding decreases. So for beryllium, it was at the 3rd ionization energy. He lost 1 pretty easily. He lost 2 pretty easily, but then he went down and his ionization energy was huge. For aluminum, it was at the 3rd ionization. So he lost 1 pretty easily, lost the 2nd one pretty easily, lost the 3rd one pretty easily. But after that 3rd one, for the 4th ionization energy, he went down a valence shell, and that ionization energy went way, way up. If you want to do phosphorus, you certainly could. He'd give up 1, he'd give up 2, he'd give up 3, he'd give up 4, he'd give up 5. But then he'd be down a valence shell, so trying to take that 6th electron would be next to impossible. He went down a valence shell. All right, one final trend to talk about here. We'll wrap these notes up. I'm going to take a shortcut on this. All right, so electron affinity. Again, this one means love. How much do atoms love electrons? We're asking how much energy is released when an atom gains an electron. So there's 2 ways to make an ion. You can either remove electrons like we're doing here, that's ionization energy, or you can add electrons. And then you have the measure of how bad an atom wants to add an electron affinity. All right, so I'm gonna cheat just a little bit. Let's take a look at fluorine. So here's fluorine, 2 electrons shielding the nucleus, 7 valence electrons. All right, I'm going to compare fluorine to bromine right here, number 35. Again, here's where I'm kind of cheating. Instead of drawing all 28 electrons, I'm just going to write that there are 28 electrons shielding the nucleus. And then draw the valence shell. So at first glance, these are really similar atoms. They both have 7 valence electrons. They both, you could say, really want that last. If I threw an electron in between them, they both really want it. But fluorine is going to want it more. Fluorine will have the higher electron affinity because it's not protecting its nucleus. That nucleus is exposed, +9. I'm not saying bromine won't want it, but he isn't going to want it as bad as fluorine. Fluorine has, again, 9 protons that are not very well shielded. No one's really repulsing that electron. Over here, we've got 28 inner shell electrons that are basically saying, no, we don't want another electron. They're negatively charged. Negative charges are bad. Don't give us another electron. Just a small heart for bromine, big heart for fluorine. His electron affinity is going to be much higher. As you move down a group, the electron affinity is going to decrease. The amount that that atom wants that electron is going to decrease because of increased shielding. All right, so that wraps up our Unit 5 notes. Means we got a test on the horizon, so make sure you guys are taking a look out for that, looking at the review, looking at the homeworks. Come in when you can for review if you can. But that wraps up our notes. So I'll see you when we start the next chapter next week. See ya.